Bonding bushings are required at the following locations: firstly, between the utility disconnect and meter base, and secondly, between the meter base and the load side disconnect. Yes, it is acceptable to make a tap at the load side disconnect for the transformer, provided that the following requirements are met. Firstly, the tap conductor must be rated for the full load of the transformer. Secondly, the tap must be made using a lug rated for the size of the tap conductor. And thirdly, the tap must not reduce the ampacity of the conductors supplying the motor. The overcurrent protection in the load side disconnect must be sized as follows. Firstly, for the motor, at 125% of the motor's full load current, which is abbreviated as FLC, and secondly, for the transformer, at 125% of the transformer's rated secondary current, which is abbreviated as RSE. The FLC and RSE can be found in the motor and transformer datasheets respectively. All equipment must be weatherproof or rainproof. All conduits must be properly supported and grounded. All wiring must be in accordance with the National Electrical Code. The installation should be inspected by a qualified electrician before energizing. Let's delve into these topics in more detail, starting with bonding bushings. Bonding bushings are essential components in electrical systems, particularly where metal conduits or enclosures are used. Their primary function is to provide a reliable electrical connection between different metallic parts of the system, ensuring a continuous ground path. This is crucial for safety, as it helps to minimize the risk of electrical shock and prevent the buildup of static electricity. When a fault occurs, such as a short circuit, the bonding bushing provides a low impedance path for the fault current to flow back to the source. This allows the overcurrent protection devices, such as circuit breakers or fuses, to quickly detect the fault and trip, disconnecting the circuit and preventing further damage or hazards. The NEC mandates the use of bonding bushings in specific situations, particularly when dealing with service entrances, equipment grounding conductors, and metal raceways containing service conductors. The specific requirements can be found in NEC Articles 250.92 and 250.97. In the context of this installation, bonding bushings are required at two key locations. The first is between the utility disconnect and the meter base. This connection ensures that the meter base is properly grounded to the service equipment, providing a safe path for fault currents. The second location is between the meter base and the load side disconnect. This connection ensures that the load side disconnect, which feeds the motor and transformer, is also properly grounded, protecting the downstream equipment and personnel. When selecting bonding bushings, it is important to choose the correct size and type for the application. The bushing must be compatible with the size of the conduit or enclosure, and it must be rated for the appropriate voltage and current. It is also important to ensure that the bushing is properly installed with a tight and secure connection to both the conduit and the grounding electrode conductor. Now let's discuss the tap at the disconnect. Tapping conductors is a common practice in electrical systems, allowing multiple loads to be supplied from a single set of conductors. However, it is important to follow specific guidelines to ensure that the tap is safe and compliant with the NEC. In this case, a tap is being made at the load side disconnect to supply a 2.5 kVA transformer. The transformer will then feed a 20-circuit panel for single-phase loads such as control circuits, lighting, and receptacles. According to the NEC, a tap is permitted under certain conditions, as outlined in Article 240.21. These conditions are designed to protect the tap conductors from overcurrent and ensure that the overall system is safe and reliable. In this scenario, the tap conductors must meet three key requirements. Firstly, the tap conductor must be rated for the full load of the transformer. This means that the ampacity of the tap conductor must be equal to or greater than the rated primary current of the transformer. To calculate the transformer's primary current, you can use the following formula: volt amps divided by volts. In this case, the transformer is rated at 2.5 kVA, which is equal to 2500 volt amps. The primary voltage is 480 volts. So, the primary current is 2500 volt amps divided by 480 volts, which equals 5.21 amps. Therefore, the tap conductor must be rated for at least 5.21 amps. Secondly, the tap must be made using a lug rated for the size of the tap conductor. This ensures a secure and reliable connection between the tap conductor and the main conductors. The lug must be properly sized for the conductor, and it must be installed according to the manufacturer's instructions. Thirdly, the tap must not reduce the ampacity of the conductors supplying the motor. This means that the main conductors must be sized large enough to carry the combined load of the motor and the transformer without exceeding their ampacity rating. To determine the required ampacity of the main conductors, you must add the motor's full load current to the transformer's primary current. The motor's full load current can be found on the motor's nameplate. In addition to these requirements, it is also important to ensure that the tap conductors are properly protected from physical damage. This can be achieved by running the tap conductors in conduit or other suitable raceway. Finally, let's discuss overcurrent protection sizing. Overcurrent protection is a critical aspect of electrical system design, protecting equipment and personnel from the hazards of overloads and short circuits. The NEC provides detailed guidelines for sizing overcurrent protection devices, such as circuit breakers and fuses, to ensure that they will properly protect the circuit. In this installation, overcurrent protection is required in the load side disconnect for both the motor and the transformer. For the motor, the overcurrent protection must be sized at 125% of the motor's full load current. This is in accordance with NEC Article 430.52, which allows for a higher overcurrent protection rating for motors to accommodate their inertia current during startup. To determine the motor's full load current, you can refer to the motor's nameplate or use the tables in NEC Article 430.250. For example, a 40 horsepower, 480 volts, three-phase motor has a full load current of 52 amps, according to NEC Table 430.250. Therefore, the overcurrent protection for the motor should be sized at 125% of 52 amps, which equals 65 amps. You would typically use a 60 amp or 70 amp circuit breaker or fuse, depending on the available standard sizes. For the transformer, the overcurrent protection must be sized at 125% of the transformer's rated secondary current. This is in accordance with NEC Article 450.3, which provides guidelines for overcurrent protection of transformers. To determine the transformer's rated secondary current, you can use the following formula: voltamps divided by volts. In this case, the transformer is rated at 2.5 kVA, which is equal to 2500 voltamps. The secondary voltage is 240/120 volts. Since the transformer has two secondary voltages, you must calculate the current for each voltage separately. For the 240 volt secondary, the current is 2500 voltamps divided by 240 volts, which equals 10.42 amps. Therefore, the overcurrent protection for the 240 volt secondary should be sized at 125% of 10.42 amps, which equals 13.3 amps. You would typically use a 15 amp circuit breaker or fuse. For the 120 volt secondary, the current is 2500 voltamps divided by 120 volts, which equals 20.83 amps. Therefore, the overcurrent protection for the 120 volt secondary should be sized at 125% of 20.83 amps, which equals 26.4 amps. You would typically use a 25 amp or 30 amp circuit breaker or fuse. It is important to note that these are just general guidelines, and the actual overcurrent protection sizing may vary depending on the specific application and the manufacturer's recommendations. Always consult the NEC and the equipment documentation for the most accurate and up-to-date information. In addition to the above considerations, there are several other important factors to keep in mind when installing electrical equipment outdoors. Firstly, all equipment must be weatherproof or rainproof. This means that the equipment must be designed to withstand exposure to the elements such as rain, snow, and sunlight. Weatherproof equipment is typically rated for outdoor use and is constructed with materials that are resistant to corrosion and degradation. Secondly, all conduits must be properly supported and grounded. Conduits provide physical protection for the conductors and also serve as a grounding path. They must be securely supported to prevent them from sagging or breaking, and they must be properly grounded to ensure that they can safely carry fault currents. Thirdly, all wiring must be in accordance with the NEC. The NEC is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment. It is important to follow the NEC guidelines to ensure that the installation is safe and compliant. Finally, the installation should be inspected by a qualified electrician before energizing. A qualified electrician can verify that the installation is in accordance with the NEC and that all equipment is properly installed and functioning. This can help to prevent potential hazards and ensure the safety of personnel and equipment. In summary, the installation of a new service for an electric pump requires careful attention to detail and adherence to the NEC. By properly sizing bonding, bushings, transformers, taps, and overcurrent protection, you can ensure a safe and reliable electrical system.